You're ready.
Okay. So my name is Chris Danforth, and I am an applied mathematician at the University of Vermont. I work on a variety of big data problems. The one of which that's relevant today is trying to understand how to predict the future state of the Earth's atmosphere and climate. And so today I'm going to talk a little bit about how the Lorenz equations and my research involving the Lorenz equations contributes to that discussion. So we're going to begin with some background motivation. So here is a picture of
You have to share your screen.
North America. I have to share my screen. Stop webcam. Share my screen. Thank you for the helpfulness. So here we go. Can everybody see that? Yeah? No? Okay. So this is a picture from the cover of Eugenia Kalnay's book. And you're looking at North America, and what you see are spaghetti curves, what we call them are spaghetti curves. They're different versions of the jet stream, where the jet stream is. And actually, one of them is where the jet stream actually was 5 days after this forecast started. And the rest of them are forecasts of where the jet stream would be those 5 days later that are based on slightly different initial conditions of the numerical weather model. So we call it spaghetti because in some regions you can see it's doing quite well. So this ensemble is agreeing with itself remarkably well over the United States. And it's not agreeing so much over the North Atlantic, but over the North Atlantic the spread happens to be in what we would call a low-dimensional subspace. So it's like somebody stuck the fork in and spread it out along a line of longitude. And that's something we take advantage of. But this particular picture is remarkable because this was about 20 years ago that this forecast was run, and it was the first time that the National Weather Service was able to predict a snowstorm for the Mid-Atlantic region near you guys right here 5 days in advance. So you have the jet stream, of course, has the cold air above it from the Arctic and the warm air below it. And you have so this pressure system sitting in here that's spinning this way and pulling moisture in off of the Gulf of Mexico and off of the southern eastern Atlantic of the United States and creating this snowstorm here in the Mid-Atlantic. That's what the prediction was, and it turned out actually to be the case. So we, as people who understand dynamical systems, are in a position to do things like this, right? We take big computer models and make simulations from them and then try and understand how well do those simulations compare with reality. So that was 20 years ago. A more relevant recent example is hurricane modeling, and in particular Hurricane Katrina. So what I'm showing you now is this cone of uncertainty that you all living in North Carolina are very familiar with. So the way they do this, they have a bunch of hurricane models, sometimes using different physics and sometimes using different conditions of the atmosphere around the center of the hurricane. They run them forward, and most of them take some sort of a curve near the middle where this black curve is. That's how it's defined. Most of the forecasts say the hurricane is going to do this. And, you know, some of them wander off into the Atlantic, some wander off into the Gulf, over towards Mexico, but most of them do this, right? So they create this cone of uncertainty, great phrase. And what they don't typically do is show you the cone of uncertainty after the hurricane has already passed. Typically they show you what they think is going to happen over the next 5 days. And in this case, this is Hurricane Katrina's forecast about 3 days before it struck the coast of New Orleans. And you can see from, I've drawn the path that the hurricane actually took, you can see that it is not in the cone. So this is bad news, and we as dynamical systems people working in this field, we try and understand why things like this happen and how to avoid it, techniques we can come up with. But of course, the hurricane model is incredibly complex, and it's hard to go in and dial a couple knobs and see why the hurricane predictions didn't follow this track. So what we do typically is we try and develop techniques that help forecasts on low-dimensional systems like the Lorenz equations. And if they work, if we can figure out ways to forecast problems in those systems, and then we can scale them up and try them on bigger phenomena. Any questions so far? Okay. So I'm going to move on now to the Lorenz equations, right? So let's see. So where are we? So you guys have talked about the Lorenz equation. So Ed Lorenz was this meteorologist working in the 50s and 60s at MIT trying to demonstrate to the National Weather Service that these linear methods of prediction, they weren't going to work for weather forecasting. And so he settled on this model of convection. And what I'm going to talk to you about today is our efforts to understand, how to translate findings in that simple model of convection to the actual atmosphere, the big, hairy, nonlinear, billion variable weather model. So Lorenz's idealized system was this Rayleigh-Benard convection cell. It's at its simplest supposed to represent what happens with the Earth, right? So the sun the energy from the sun comes in and heats up the surface of the Earth, and that energy is re-radiated up into the atmosphere, and the warm air rises, and eventually it gets cooled off by the air above it, or space, if you will. And so this makes the air want to sink, and then it gets heated up and wants to rise, and so you get these convection cells. And so Rayleigh-Benard convection is a well-studied problem where you try and understand in a little two plates, a cold plate on the top and a hot plate on the bottom, and you can vary things like the aspect ratio and the temperature difference between the two plates, and all kinds of incredibly interesting nonlinear phenomena happen in the atmosphere. This is what produces thunderstorms. Okay, so we when I was an undergraduate at Bates College, I built a version of this that was supposed to be even simpler than Rayleigh-Benard convection, and it's called a thermosiphon, a thermal convection loop. I'm going to show you a picture of it here. So the idea is it's a hula hoop that's oriented vertically. It stands up. It's roughly the size of a hula hoop. And what we do is we apply a heat source along the bottom half of the loop on the outside, either with a bath or heating tape wrapped around it. And then a heat sink, so some sort of cool, you can use just room temperature air with a fan blowing on it, or you can actually have a cold bath on the top half. And the system, if you create a small temperature difference between the bottom half outside and the top half, and there's water on the inside, since it's oriented vertically, let me show you a picture of what it looks like. So here's a closed off one, and me standing in front of it, and these are little temperature thermocouples that we use to measure on what's going on inside of it. So that's what it looks like. So what happens when you turn on the temperature difference? Well, the fluid is going to conduct heat initially, right? So at small temperature differences, the fluid in the bottom half starts to heat up, and the fluid in the top half starts to cool down, and they just kind of bounce around for a while. And the temperature difference, the main thing that we like to plot is the difference between, let's see if I have a picture of it, maybe it's here. So we plot the temperature difference between points A and B in the loop. And the temperature at point A minus the temperature at point B is going to be positive. That difference is going to be positive if the fluid is rotating in the clockwise direction, because stuff's cooling off, and then it gets to point B and it starts heating up and heating up and heating up, and it gets to point A and starts cooling off. And so the stuff's coolest at point B and warmest at point A. So this variable that we measure in the device, one of them is the difference in temperature between points A and B. And as I was saying before, if you have a small enough temperature difference between the bottom half and the top half of the loop, then the fluid conducts. It doesn't rotate, and the temperature difference between points A and B is effectively zero. It kind of bounces around zero. And this is real data that I took from this device that I built as an undergrad. And we call this stable conduction. And I'm going to show you what this looks like in the Lorenz equations. So what I've done here is, so there's this built-in intrinsic MATLAB demonstration called Lorenz, but I've gone in and modified the code. So here you see the parameter rho in Lorenz's equations. Let's see what that parameter corresponds to. So Lorenz's equations, I got them in here somewhere. So dx dt, dy dt, dz dt. You guys have seen this. It's a weakly nonlinear system. You got three variables. You need three variables to have chaos in a differential equation. Two won't do it because you get just sinks and sources and saddles in 2 dimensions. So so you have these variables. The x variable is just proportional to the velocity of the bulk velocity of the fluid in this loop. The y variable is proportional to the temperature difference across the loop. So that would be the difference between the temperature at point A minus the temperature at point B. And then the z variable is a little more complicated. You take the conducting temperature profile, where it's just warm on the bottom and cool on the top, and then you aggregate deviations over that. So you integrate over all the heights in the loop, and you see how much is the state in the loop deviating from just its regular conducting, no movement profile. So those are the three variables, x, y, and z, and there are these parameters that we ought to at least mention. So the parameters in Lorenz equations, you have a geometric parameter b related to the aspect ratio of the loop. So in our case, I think the inner radius is 1/30th of the outer radius. It's about a meter or half a meter radius loop. The Prandtl number is the dimensionless ratio of viscosity to thermal diffusivity. So that measures whether things are being transported more by this movement or by the conducting of the energy. So how is the energy getting moved around? And then the Reynolds number, and this is the most important parameter, and it relates to the forcing, right? So how much energy are we putting into the bottom half? How much are we taking out of the top half? And as you dial this Reynolds number up, you get more interesting behavior. So those are the details. And if you go in MATLAB, you can run this Lorenz simulation, and I'm just going to show you what happens. All right. So I'm just going to press start, and this is going to pick a random initial condition with a forcing for this system that is very small. And there are three equilibrium solutions to Lorenz's equations. The one at the origin corresponds to conduction in this system. So the simulation we just ran, it's still running. Stop. Start it again. This simulation is starting with a random initial state. So the fluid is spinning around and has some strange temperature profile. And then we ask it, all right, in the future, what happens for a very small forcing difference between the top and the bottom? And the answer is that the fluid comes to rest. In the Lorenz equations, that's at the origin, x, y, and z equals 0. And at that point, we have, if you looked at the Jacobian and its eigenvalues, you'd get three eigenvalues that have negative real part. So anything nearby, and in this case, anything anywhere near, anything in the entire state space converges to that equilibrium. So conduction is a stable state. And again, that corresponds, so I could do this a few times. I start with an initial condition. It'll always do this. It'll go to the origin. That corresponds to this state where we have it's not so much hotter down on the bottom than it is on the top, so things aren't moving around very much. And this is a stable state. So if I started with a temperature difference that was big up here at 5, it would just decay down to this. So all motion stops. Okay, so that's like the baseline situation for Lorenz. Let me pause again and ask if there are any questions so far. All right, so I want you to imagine that you're an undergraduate student. You're standing in front of this loop. I got tubing from Lowe's or Home Depot for this thing, and taped it together with duct tape. And I start to crank up the heating tape forcing on the bottom half. So I'm making it hotter, and you see a bifurcation happens where the conducting equilibrium becomes unstable. So fluid is warming up in the bottom and cooling off in the top, and eventually buoyancy overcomes the friction, and it picks a direction to rotate in. So mine was biased, so it always rotated initially in the clockwise direction. The one we're building ought to be machined well enough so that there is no bias, or the bias is very small. So what you see here is a full hour worth of temperature difference. That is the temperature between points A and B. So temperature at A minus temperature at B for a whole hour. And for the whole time, it's roughly 1 degree different. And what that means is that the fluid is rotating with a period of roughly, it would take maybe 45 seconds or a minute for it to go all the way around. But it's come to a steady state. So there's this, it's kind of weird. You got to think of this. The fluid is in a steady state in the sense that the temperature at point A minus the temperature at point B is at an equilibrium. It's fixed, or it's oscillating with very small amplitude, and even though the fluid's moving. So it's an equilibrium state even though the fluid's moving. So let's look at what that looks like in the Lorenz equations. I'm going to go into the code here and modify the forcing for stable convection, and we'll run this again. Go. Okay. So this is now, according to my poorly commented code, going to be a stable state of convection. And so you're used to seeing the thing oscillate around like this. Sometimes what happens is it gets into a state where it'll oscillate around for a while and exhibit what we call transient chaos, where it doesn't settle down quickly. And I'm expecting that that's what's going to happen here. So this particular initial condition appears to have a transient period that's interesting. And if we let it go for a while, what I expect will happen, since the forcing we offered is in this regime of stable convection, is that even though the fluid's oscillating and spinning around for a while, it'll eventually settle down, and this trajectory will dive in towards one of the stable equilibrium convecting states, and it appears to have done so. So I'm going to leave here for a second. We'll let it run. I'm going to leave here and go back to what data we have from the experiment, and say that what just happened, what you would have just seen if we plotted it on this figure, is the temperature difference oscillating around here for a while, growing in amplitude, and then the fluid switching direction, oscillating around this equilibrium for a while, switching direction, it did it 3 or 4 times, and then eventually settling down. So we call that transient chaos. I can find another picture of it in here for you. Here's what it looks like when you plot it for a long trajectory. And so you see that for a while it's drawing out this beautiful butterfly shape, and then eventually it gets too close to this equilibrium state, which it turns out is just very weakly stable. So if you look at the Jacobian eigenvalues, there's going to be a couple that are very negative, but one that's negative but very close to 0. So it takes a long time for this trajectory to wind its way in. My computer is humming. I don't know if you can hear that, but it's still. Oh, look at that, beautiful. So the trajectory has dived in. This is where it started right here. And it's oscillating around it, and so this is one of those convecting equilibrium solutions. It's just weakly stable, so it takes a while to get there. There's another one over here that it just as easily could have found. Amazingly, if you take this forcing parameter R, which in the experiment, again, is the temperature difference between the top half outside forcing and the bottom half, and that's something we fix at the beginning of the experiment. That's not something we're dialing during the experiment. So we fix it at that value, and if you crank it up just a tiny bit more, the incredible thing that happens is that these transients last longer. So there's this bifurcation that happens, of course, when it gets a little bigger. But as you approach this transition from these two equilibrium being stable to unstable, the transients just last longer and longer. And I think the caption in this picture says something about it. So let me find it for a second. So for R equals 23, the mean lifetime of this transient chaos is about 300. As you crank it up a little bit more, the mean number of oscillations becomes 2,400. And as R is chosen, that's the Rayleigh number, the difference in the forcing, as it's chosen closer to the critical value, the number of oscillations increases so that it becomes increasingly difficult to distinguish between a chaotic attractor and just transient chaos. And even at R equals 23, which is a little backed off, there are chaotic trajectories that oscillate chaotically forever, never spiraling into the equilibrium. So those are regions of state space that don't ever approach the basin of attraction of these two stable equilibrium. And so it's hard sometimes to tell which case you're in. Okay, so that's the story for stable convection. All right, so does anybody have any questions about stable convection?
I think we're good.
I think we're good. All right, so this is, I'm an undergraduate. Go ahead, Andrew, is there something else? All right, so I'm an undergraduate standing in front of my device, and this is boring behavior that I'm observing. I have found an equilibrium solution, and I don't have any chaos. So I turn the knob up as far as I can go, and eventually I get this behavior. So here is, for my experiment, the chaotic attractor, at least in one variable, so temperature difference. This is the y variable in the Lorenz equations. You see it's oscillating back and forth so that it's going in one direction, speeding up and slowing down, and then eventually it switches and goes in the clockwise direction, and it accelerates and decelerates in the clockwise direction for a while, and then it changes direction back and forth a few times, and then settles in again. And this is the type of nonlinear behavior characteristic of the Lorenz equations that's interesting, and that we try and understand. So if I go back to the Lorenz simulation and I change my rho value to 28. That's the typical value for that you would have played with if you've used done this sort of thing before. That is not what I want to see. Okay, there we go. So now it's going to spin around, and notice it's going nowhere near this conducting equilibrium down here. 0, 0, 0, where the fluid is motionless, being heated up at the bottom and cooled off at the top. That is, for a large forcing, a very unstable state. So if you look at the Jacobian, the first eigenvalue, the largest real part one, will be large and positive, so that it won't spend any time near this state, near the origin. That's very, it's strongly repelling equilibrium. And now there are these two strongly repelling convecting equilibrium in here. So there's been a bifurcation where these two convecting equilibrium, which are the rotating stably in clockwise or counterclockwise directions, that's the physical interpretation, those two states have become unstable. So it's not going to come to rest like it did before. It's gonna follow a trajectory where it's always deviating from, it's moving away from, it's kind of the opposite of gravity. It's moving away from one of these equilibrium solutions until it gets pulled into a region of attraction of the other side of the attractor, and it spends some time in there, always increasing its amplitude. You see that the yellow is always outside of itself with respect to the center, and it'll repeat this forever, never repeating. Okay. And you'll learn about things like Lyapunov exponents, but the interesting thing here is if we put a little ball in state space, if I imagine I took every single, you see this little red dot, if I took all of the points in that red ball and integrated them forward in time, after about 2 or 3 minutes in this simulation, they would be all over the place, right? That's the sensitive dependence on initial conditions that Lorenz was trumpeting when he wrote this paper, Deterministic Non-Periodic Flow, in 1963. So that's the interesting thing in the model. Let's look at what it looks like in this experiment. So here it's oscillating in one direction and then the other. Why does it do this? Okay, so let's try and understand why this happens. So I want you to imagine that the fluid is in this stable convecting equilibrium. Let's say it's going in the clockwise direction. And a small pocket of fluid arrives at this point A a little bit hotter than it should be due to some sort of thermal anomaly that it experienced along the bottom half. So that little hot pocket of fluid exerts an accelerating force that speeds the fluid up a little bit. That's what this arrow is meant to represent. So the pocket this tiny little pocket is a little buoyant compared to what it was last time around the loop, and it accelerates the fluid. Okay, so this little warm pocket is now traveling through the cool section warmer than it was last time. So since it sped the fluid up, it spends less time cooling. All right, so we have a warm pocket that spends less time cooling. So when it gets over here, it's warmer again than it should have been and than it was last time. And warm things like to rise. Now the fluid is carrying it around in the loop due to its momentum, but it wants to rise because it's warmer than it should be and warmer than its neighbors. And so it decelerates the fluid, and that's what this little arrow is meant to represent. So we have a little anomaly that has accelerated the flow and now decelerated the flow. It's still going in the clockwise direction, but it's sped up and slowed down. And now, since it's slowed down, this warm pocket spends more time heating as it comes through the bottom half of the loop. And again, when it gets over to point A, it's hotter than it should be and even hotter than it was last time. So it accelerates the fluid even more. That's a positive feedback. That's why this arrow is longer. It spends less time cooling as it goes through the top half of the loop. And when it gets over to this point, it's even cooler than it's even warmer than it should have been last time. And it wants to decelerate the fluid even more, even though the bulk is moving in this direction. And that's why this decelerating arrow is pointing back up. Hot things like to rise. This thing is sinking. It's a hot thing that likes to rise and it's sinking. So it decelerates. Spends less time on the cooling. Now it's decelerated the fluid. It will spend more time heating up again. Positive feedback, longer arrow, less time cooling, more deceleration. And so these arrows get bigger and bigger until eventually the fluid just switches direction. So that's, if we now look at one of these typical Lorenz trajectories, which I've annotated, we know what the equilibrium states are. They're square root of b times r minus 1. Analytically, we can figure that out. These are the two equilibrium at the center of the butterfly attractor. They are stable for R values less than 20-something. They become unstable after that, and a small pocket will accelerate and decelerate the flow. That's what this is what's happening here, until it reaches some critical distance from the equilibrium. And as the fluid slows down, it comes to a complete stop, just briefly, and then it performs the same increase in amplitude around the other equilibrium. Okay, so that's the mechanism in play. I'm going to show you. I'm hopefully going to show you what this looks like in an actual experiment. Imagining we could do that. This is a CFD simulation, one of these fancy implementations of the Navier-Stokes equations for fluid flow. What you've just seen happen is, if I can pause it here, pull it back. We start the fluid off at a thermal equilibrium at 300 Kelvin. Along the inset, on the inset in the center here, what you're going to see is the bulk velocity of the fluid, which is the y variable of the Lorenz equations. And we're going to integrate that in time using the Navier-Stokes equations, which have put, something like 20 or 30,000 little mesh points in this annulus. And, it's a full simulation of what goes on. So when I press play, the transient behavior will happen. It's going to spend some time near this very unstable conducting state where the fluid is just sitting there. So you'll see that things are warming up in the bottom and cooling off on the top, warming up on the bottom and cooling off on the top. And now really we're in this awful energetic state where we have really warm things on the bottom that want to rise. We have really cool stuff on the top which wants to sink. This is like when you go to the amusement park and you're in the pirate ship and you've been put upside down. All the mass is on the top. It's like if you have a pendulum and you hang the pendulum straight up in the air above its pivot, and then you're going to let it go. And it's a super unstable state, something that is in equilibrium, but you have no chance of actually finding in practice and putting it at that equilibrium because its eigenvalues of the Jacobian, evaluated at that point, large and real, positive. So we have the system sitting in this state. It is a huge storm waiting to happen, and once it picks a direction to rotate in this case, it's going to be counterclockwise. It goes very rapidly through this counterclockwise rotation. You can see how in a second all of the warm fluid that used to be on the bottom half is now moved from 12 to 6 o'clock, and all the cold fluid is from 6 to 12 on the other side. Got a question? Okay. Okay, so can you turn on your mic, Andrew, so I can hear Raj?
Raj isn't here.
Raj, okay. Read me the question again, Lewis.
Why are the sides warmer than the very bottom?
Let me go back to the beginning. Okay. Very good. So Raj's question is, why are the sides warmer than the very bottom? So I think what he means is that you can see how the edges of the loop are warmer than the interior, right? Because it takes time to heat up. But he's saying that over here, the temperature is much warmer in the middle than it is, let's say, down here. So my answer is going to be kind of off the cuff, but my guess is that the fluid down here is not mixing very much because there's nowhere for it to go vertically. Hot stuff wants to rise, and there's really nowhere for this hot stuff to rise down here at the bottom. This is like a little mini Rayleigh-Bernard cell right down here. So the geometry forces it to sit there and not really mix. Over here, you have the warm stuff, so you're heating on the sides, but it is allowed to move vertically like it wants to. And so I think that the mixing, in answer to Raj's question, I think that the mixing is responsible for why it gets really warm at the sides quickly. You also see more sort of eddies and turbulent energy transfer happening, pulling off of the wall in this little region at the initial stages. Does that answer your question, Raj? Great.
Yes.
Great. Okay. All right. So let's look at this. Let's see what happens. So I was saying it goes through one oscillation. So the fluid is heated up to this super unstable conducting state. So that would be the origin in the Lorenz equations. It is going to pick a direction to rotate in, and once it does, its velocity is larger than it typically ever is because it's a transient state, and it really ends up in the situation it's pretty happy with in this case, where you have the warm stuff on the top and the cool stuff on the bottom, which is the way fluids like to be, right? Hot stuff rises, cold stuff sinks. but it's exactly the opposite of the forcing, right? So that anomalous state will quickly change, and I'm just going to let it play through for a while here so you can see what happens now in this counterclockwise direction that it's rotating in. The amplitude of the oscillations are growing. That's not so bad. The amplitude of this oscillation is growing. It's always going in the counterclockwise direction, but it's speeding up and slowing down. So now it's at its fastest, slowing down. Now it's at its slowest, at its fastest again. And now it comes to a point where it's the amplitude of this oscillation, so it's growing and growing and growing. That amplitude of that oscillation would just continue to grow if it weren't for the fact that physically it's impossible. So it has to turn around and go in the other direction. And so at this point, the fluid stalls for a second and then changes and goes clockwise. It takes one big swoop through and then turns back around and goes counterclockwise. So there's a whole lot to say about what's going on here, but I think the main takeaway that I'd like for you to have is that here we have a computational fluid dynamics simulation of something that's going on in a fluid that's clearly highly nonlinear. There are little turbulent vortices in here. There are Kelvin-Helmholtz waves breaking along the walls. There's all kinds of mixing, stuff that's actually really quite nonlinear and local. But if you take a bulk quantity to characterize the fluid, like just the average velocity at the center line around the loop, and that's what we're plotting on the inside here, we get something that's actually quite smooth and looks exactly like what a Lorenz equation trajectory would look like. So from our perspective, this is amazing because we use this now as a test bed to try and develop techniques to do prediction of the atmosphere of other systems that are of interest to us. So that's one animation. Let me show you one more. In this case, where there's some transient chaos, but the forcing, in fact, is actually in this case going to require that the convecting equilibrium is stable. It's just going to spend a long period of time in a transient state. And in this particular case, it's kind of hard to believe, but this forcing difference between the bottom half and the top half, it undergoes these bifurcations, and eventually if it gets too big, the forcing difference, it becomes stable again. So as you crank up the heating and heating and heating and cooling, it exhibits this chaotic behavior for a while, but if you crank it up so much, then the fluid really just doesn't have any time to cool off or heat up, and it just settles into a convecting equilibrium again. So as you dial this parameter R, you spend some time in a chaotic regime, but then as you make it even hotter on the bottom and cooler on the top, it becomes stable again. So this is now what stable convection would actually look like if we could see a cross-section of the loop. There would be these little thermal fluctuations that you can observe and velocity fluctuations, but really it is quite stable. So let me pause again and see if there are any questions. Okay, Raj is typing. How long did the simulation take is Raj's question, the CFD simulation. So, let's look down here on the axis and see what our flow time is for one of these guys. Our flow time is 3,000 seconds. So what is that, like, how many seconds? So that's an hour? Is that an hour? So we're simulating, which is not far off from what this data. This was an hour long. The CFD itself, this is what you're looking at here is a two-dimensional simulation where we pretend that we have two annuli, so cylinders that go off towards infinity, in towards the screen and out at you, and that simplifies the number of locations you need to pay attention. We also have simulations fully in 3 dimensions where we actually simulate the full loop, and it's more like 10 million finite elements that we're looking at. So the 2D simulations are quite cheap. So something like what you see here might take an hour on maybe 4 to 8 processors, and this is a Fluent. We use Fluent, but we're switching over to this open foam, open source software for CFD. The three-dimensional simulations take much longer. So simulating 300 seconds of fully direct numerical simulation in 3D, that takes more like a day to do something like this on 8 to 16 processors. Does that answer your question, Raj? Okay, great. So I just want to show you a couple other example trajectories. Here we're plotting the area-weighted average mass flow rate, which is effectively this this velocity that we were just talking about. And it does some very non-Lorenz-like things for particular values of this forcing. So in some cases it'll have a big transient and then settle down. So the trajectories on the bottom here are much more Lorenz-like. There are also situations where the equilibrium state looks like it's going to give up. So there's this beating pattern where it gets bigger and smaller. We don't understand why that is. There shouldn't be any asymmetry, so that the fluid shouldn't spend any more time on going in one direction than the other, but we see that happening sometimes. So we're investigating all sorts of these behaviors, and here's an example bifurcation diagram where the two dials that both contribute via some manifold to this Reynolds number are the flux, so that's how much energy are you putting into the bottom half and pulling out of the top, so the more energy, the more you're driving it. And gravity, so the more gravity is there, the harder it is to get hot stuff to rise. And so you have stable convection when the energy being put in is very low. So those are these red squares. Unstable convection is, the interesting Lorenz butterfly type stuff that I was showing you before. And then I showed you one simulation where we were in such a high energy regime that it settled down again for convection to be stable. Okay, so let's see. Is there anything else I wanted to show you? Oh yeah, okay. So I can show you at least in the Lorenz equations what the bifurcation diagram looks like. So here is a bifurcation diagram for the Lorenz equations. Lorenz did this really cool thing with the z variable, which I didn't mention much, but he basically looked at successive values of the z variable of the Lorenz equations, and I can show you what a trajectory of the z variable looks like here. So this is what a trajectory of the z variable looks like. It's all, say, between 15 and 50 going up and down, but it doesn't exhibit the same sort of regime change type behavior that the x and y variables do, where they spend time going across 0. So, all right, so Lorenz's z, he looked at successive z maxima and found that that they exhibit, that just that one variable exhibits chaotic behavior. And here's a bifurcation diagram of it. So, so anytime you see a dot in one of these bifurcation diagrams, that means that the fluid is spending significant amount of time near that state, and it's doing so, indefinitely. If you go out all the way to infinity, it's spending most of its time there. So this is really a sink. And what you see here is that it's left off this figure, but for R values less than 25, it's just 1 point on the dot. So since it's z, it's not counterclockwise and clockwise both produce the same z. So it would be 1 point right around here, and then that bifurcation happens, and this is chaotic behavior where we're going around the butterfly. There's some periodic windows in here, which are incredible stuff. There's this periodic cascade down towards another periodic window that happens for R. And then in the very high energy regime, there can be periodic behavior where the fluid its amplitude is oscillating, but doing so in a periodic fashion while always going in one direction. And then at the highest energy, settling down into stable convection again. But for all of these values, conduction is a super unstable equilibrium state. Okay, any questions about that? All right, I got maybe 5 minutes to go, so I just want to show you one other cool thing we're doing with this. Okay, so some of you may have heard of Eureka, which is this software program developed by a couple computer scientists at Cornell, Hod Lipson and Mike Schmidt. And what's amazing about this software program, they call it the Robot Scientist, is that what they do is they, in this example I'm showing you, they took a double pendulum, which is one of the hallmark nonlinear systems that we understand quite well but can't predict for more than, say, 5 seconds given the equations due to the nonlinearities and how chaotic it is. They took one of these double pendulum with a little driving frequency attached to the center, and they just had a laser shine on the double pendulum and observe its position. So they took this big bag of data of pendulum position for like an hour, and then they fed it to one of these evolutionary computing algorithms. And the way that works is they have a candidate bag of differential equations that knows nothing about physics. Doesn't know that there should be sines or cosines or angles involved, or powers of the variables, or how they should be combined, or that there are parameters. All it knows is that there's this big bag of basis functions: sines, cosines, exponentials, operators, plus, minus, divide, times. And what the software does is it mimics evolution by combining these equations, differential equations on the right-hand side, let's say 50 different models for what's going on with the double pendulum. And then so they test those differential equations, how well they model the system. And the equations that model the system well, they keep those and mutate them by moving terms around, changing parameters, and create a new set of equations. And they apply those equations to the data and see which ones work well. And the ones that don't work well, they throw them away. The ones that do work well, they keep them. And they perform this procedure over and over again. And there are very intelligent computer science ways to avoid getting stuck in local minima in that sort of a evolutionary process. And what they end up with, you can listen to Radiolab. You should all listen to Radiolab if you're not listening to it. They talk about this. They end up with the equations of motion of the pendulum in about 5 minutes. So, it took differential equations, people like Newton working on these sorts of things for years to understand how to derive from first principles what was going on in this system. And it took this software program just a few minutes to figure it out. So this is unbelievable. And I'm going to show you what it looks like for the Lorenz data. So you can download this. If you work with data, I recommend you download a piece of software called Formalize, which is the 2.0 version of Eureka. And so what I did was I just entered data observations from that CFD experiment. So the loop that you saw rotating with the cool animation, we took that mass flow rate or the center velocity and fed it in to an assimilation algorithm that kind of guessed what the other two variables will be based on that quantity. But we observed, in this case, the x variable. And so you can see this is what it looks like. And what we do then is ask Eureka to try and figure out what the equation should be for that system. And I can go back. Let me just go back and show you what Lorenz decided when he derived this from first principles was that dx dt, the rate of change, should be some parameter times x minus y. All right. So now what Eureka does is I'm going to ask it to search for potential equations that model this data very well. And so it's going to take a second for it to get its act together. But you're going to start to see it populating here with equations that describe the data. Differential equations. So this capital D is the substantial dx dt derivative. And very quickly, so just in a few seconds, I'm gonna pause this because we've already done it. You can see this is what this plot shows is the error in the fit for those differential equations versus the complexity, which is a measure of how many terms are involved. And typically what you get is, this is called a Pareto curve. You get some place where you get the most bang for your buck, and then you get some diminishing returns that overfit the data substantially. So this red dot here is this really complicated equation involving x, y, y, z, z, y, and some constants. But this term right here, the one I want to draw your attention to, at complexity 7, right here, is dx dt equals 0.313y minus 0.309x. So if I pull a 0.3 out of here, it's y minus x, 0.3y minus x. So negative, if we do y minus x, the negative in front of sigma cancels out. And just in 3 seconds, what I've shown you is that Eureka can find the differential equation describing dx dt for this system. And the same thing works for y and z if you give it to Eureka. And we've done experiments where we try and see whether Eureka's equations, which are derived from nothing but data and no knowledge of physics, do as well as the first principles, spend 6 months of your life deriving from Navier-Stokes equations describing this system, and they are equivalent to each other in terms of how well they predict. And this is, the future of science. How do you use robotic and computerized software to suggest candidate models that you then have to figure out what they mean? But this is the way things are going, and I just wanted to expose you to it if you haven't seen it already. So that's it for me. We have, let me just go real quickly to the very end of my slides here. Big piles of tweets. And thank the people involved in this work. So this is my research team here at UVM. You may have met some of these people before. They've been down in North Carolina. And we have a blog where we talk about some of our work, onehappybird.com. We have a whole separate project where we collect all the public tweets and are developing a remote sensor of global well-being based on words that people say in line with GDP and consumer confidence. And okay, so I'll stop now and take questions.
There don't appear to be any questions.
Okay, well, if anybody has any questions that they don't want to share publicly, you could email me or go check out our blog, onehappybird.com. Raj is typing. Very good. Okay, team. Thanks very much.